Today we are talking about a critical challenge and an incredible opportunity for steel industry. Forging a green future. Now steel is essential for modern life, but its production comes with a significant environmental cost. Iron and steel production is one of the largest industrial CO2 emitter globally. It accounts for approximately 7 to 10% of global energy related carbon emissions, releasing about 3 gigaton of CO2 annually. If you consider everything including material transport, global steel production contribute to roughly 6% of total greenhouse gas emission. The traditional method using blast furnaces and basic oxygen furnaces, which make 70% of the world crude steel, generate about 2.3 ton of CO2 for every ton of steel produced. This makes the steel industry a major player in our global climate dilemma. The essential, less invasive solution. This industry is often called hard to abate because its chemical reaction naturally produce a lot of CO2 and the challenge is growing. Global annual steel demand is expected to increase by 30% by 2050. So what's a major part of solution? Carbon capture and storage or CCS. CCS is considered one of the most effective and less invasive method to significantly reduce emission in steel sector. A huge advantage is that it can be retrofitted onto existing facilities. This means steelmakers can upgrade their current plants and protect their existing investment rather than starting completely new. The International Energy Agencies predict that by 2060, CCS will be needed for about 21% of global crude steel production, capturing an estimated 506 million tons of CO2 every year. CCS is truly a crucial strategy to tackle rising CO2 levels in our atmosphere. Now, coming to the technical maturity and emerging capture technology, the good news is that carbon capture technology is technically mature. It's been well explored, scaled, and de-risked in other industry. For example, Mitsubishi Heavy Industry or MHI has a 17 large-scale CCS references, including a plant capturing nearly 5,000 tons of CO2 daily, while large-scale CCS, specifically in the steel sector, is mostly in pilot phases. Emirat's steel plant in Abu Dhabi is already operating at a large scale, capturing over half a million ton of CO2 per year. Beyond current applications, researchers are developing exciting new techniques. These include oxy combustion technology, mild combustion, and mild OCC technology. There is also a lot of research into CO2 membrane separation from flue gas using new material like carbon nanotubes and ionic liquids and even porous carbon and graphene. Other promising development including calcium looping, chilled ammonia processes and membranes assisted CO2 liquefaction. The transformative power of carbon utilization, but carbon capture is not just about storage, it is also about utilization or CCU. This is where we transform captured CO2 from a waste product into a valuable resource. Imagine turning CO2 into something useful. For example, captured CO2 can be converted into ethanol, with companies like ArcelorMittal running pilots to do just that. It can also be turned into various chemicals and textiles. or methanol for e-fuels, as seen in Ferro-Silva project in Sweden. Even fertilizers like urea can be made from CO2. Another application is converting CO2 into liquid hydrocarbon using the Fischer-Tropsch method process. A well-known utilization method is enhanced oil recovery or EOR, where CO2 is injected into field to increase oil extraction. However, for EOR to truly count as CO2 storage, it required comprehensive monitoring. What's truly transformative is that applying CCS to biomass conversion could actually achieve a net removal of CO2 from the atmosphere. Now, coming to the navigating complexities, the cost, regulation, and infrastructure. While the technology is powerful, deploying CCUS at scale comes with complexity. High investment and operating costs are primary challenges. Additionally, insufficient financial incentive and clear regulatory framework have slowed down large-scale projects in the steel sector. CCUs require a seamless collaboration across the entire value chain, from capture to transportation to storage and finally utilization. This means government need to establish stable policies and regulations, including things like carbon pricing. The process for safe geological CO2 storage is extensive, involving a year of survey, well development, pipeline construction, and continuous monitoring. Moving CO2 can also be tricky. It faces challenges like flow instability and maintaining high CO2 purity, often above 95.5%, is crucial for efficient transport and storage. There are even concerns about the potential runway cost of UK carbon capture and storage subsidies, highlighting the financial hurdles. Now, coming to the public perception and the technology agnostic approach beyond the technical and financial aspects, public perceptions plays a role. There is a common misconception that green steel doesn't involve fossil energy in any way. These overlook the vital role of CCUS play in reducing CO2 from fossil based processes that are still widely used. It's important to build trust. Sound monitoring systems are in place for underground CO2 storage with extensive experiences from the projects in Norway. Experts advocate for a technology agnostic approach. This means deploying available and proven solutions now rather than waiting decades for solely hydrogen based alternative to scale up. In fact, the cost of deep decarbonization can actually favor mature hydrogen, which is fossil based with CCS over green hydrogen by a factor of 1.8. The traditional blast furnace is still considered by many experts as the most efficient way to produce steel, underscoring the immediate need to address like CO2 emissions. While hydrogen is seen as a key step toward decarbonization, we need to act with all available tools today. The road ahead, the net zero still by 2050. So what's the road ahead for net zero still by 2050? It requires a strong partnership and a collaboration across all stakeholders: government, industry, academia, and financial partners. Companies like MHI are aiming for carbon neutrality by 2040, and Prime Metals Technology is actively working on CO2 separation pilot to lead the industry's transition. For successes, several key actions are recommended. Government need to stimulate research into cost-effective capture technologies and techniques, identify regional storage locations, and implement industrial CCS demonstration programs. Industry need to compile inventories of production technologies, and research institution must continue R&D on improving solvents and developing new advanced materials. Scaling up renewable energy, establishing a stable policy framework and containing R&D for cost reduction are paramount.